Hey everyone, here's our math problem for today. This is an exponential Diophantine equation. Solve over the set of integers 615 plus x squared equals 2 raised to y. Let's have a little background about this problem before I ask you to solve this. Let's visualize the problem. This red curve is the graph of 615 plus x squared equals 2 raised to y. Obviously, this curve is formed by infinite ordered pairs xy, but not all of them satisfy the condition that both the x and the y coordinates are both integers. And so that is our limiting condition here. Both the x and the y coordinates must be integers for them to be considered as solution to this exponential Diophantine equation. So there are three cases that can happen here. First is when all those set of ordered pairs xy forming this red curve do not satisfy the condition that both of them are integers, then we have zero solution. Second, if the only ordered pair xy that are both integers satisfying this equation happens to be at the vertex, then there is only one solution to this Diophantine equation. And third, if there is at least one solution that is not at the vertex, then we expect even number of solutions. For example, let's say this point satisfies the condition that both x and y are integers because the graph is symmetric with respect to the y-axis. Then there is another point, negative xy, here that can satisfy this Diophantine equation. And if there's another one here, there must be another counterpart at the other side. And so we can expect even number of solutions in that case. And with that as a little background to this problem, you can now pause the video and see if you can solve this exponential Diophantine equation. Now let's solve this problem together. When we are solving for systems of equations, we want the number of variables and the number of equations to be equal to solve the problem. But here, notice that there is only one equation, but there are two variables. So many would think there are infinite solutions here. However, the condition that we are only solving this over the set of integers is equivalent to a second equation that can limit our solution. And so we are now thinking here of two conditions, the first equation and this condition equivalent to two equations in two variables, and therefore this is solvable. Let's begin first with x squared. Since x squared is an integer, then when you expand, its last digit is also an integer. We know it's not a decimal number. Let's see the pattern of the last digits of x squared for x equals 1, 2, 3 up to 10. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. When you go to 6 squared, that is 36, the last digit is the same as this. For 7 squared, it's 49, the last digit is this 9. 8 squared is 64, the last digit is also 4. 9 squared is 81, the last digit is 1. And 100 squared is 100, the last digit is 0. So, let's take all these last digits, 0, 1, 4, 5, 6, and 9. We do not have 2, 3, 7, and 8. When you add 615 plus x squared, you are also adding their last digits. The last digit of 615 is 5, and the possible last digits of x squared are all of these. Therefore, the last digit of 615 plus x squared would be adding this 5 to each of these last digits here. So let's do that. 5 plus 0 is 5, 5 plus 1 is 6, 5 plus 4 is 9, 5 plus 5 is 10, so the last digit is 0. This 5 plus 6 is 11, the last digit is 1. And 5 plus 9 is 14, the last digit is 4. Now, since this right side is equal to this, then the last digit of 2 raised to y must also be the same as whatever is the last digit of the left side of the equation. What are the possible values of 2 raised to y? Here are some of the values of 2 raised to y for y equals 1 up to 10, and we are hoping to find any pattern here. You have 2, 4, 8, 6 for the last digits here, then repeat the pattern 2, 4, 8, 6, 2, 4, 8, 6. So only 4 digits appear here. So the last digits of 2 raised to y could be any of these. 2, 4, 6, 8. Now for these two expressions to be equal, their last digits must be the same. So we are looking for similar last digits here. And those digits are this 6 and this 6, this 4 and this 4. All the rest are different. And this now narrowed down our search for the values of x and y because there are only two cases here now. The first case is when the last digit of the left side is 4 and the last digit of the right side is also 4, then they can be equal. The second case is when their last digits are both 6. Next, since 2 raised to y has a last digit of 4 or 6, that implies that this exponent y must be an even number. And as an even number, y can be written as 2 times any integer k. Therefore, this 2 raised to y can now be written as 2 raised to 2k because the exponent y is in the form 2 times k. Multiplication is commutative, so we can also write this as 2 raised to k times 2. We interchange the order of 2 and k in the exponent. And applying the converse of the power rule of exponents, this can be written as the quantity 2 raised to k all raised to the second. So we can now replace this part here by this result. And the reason why we are doing this is because we'll be forming difference of two squares if we subtract x squared from both sides of the equation. And this is now factored as the quantity 2 to the k plus x times the quantity 2 to the k minus x. So we have two factors here. The product is 615. We do not know what's the value of k. We do not know what's the value of x. Next, let's investigate the factors of 615. 615 is 1 times 615, 3 times 205, 5 times 123, and 15 times 41. That means you can equate the first factor to 1, the second factor to 615, or vice versa. You can equate the first factor to 615 and the second factor to 1. There is no restriction for x to be positive or negative. We are doing this in order to narrow down our choice for the value of k and x. And so far, we do not know yet how to do that. Now, the key insight here is if we add these two factors, 2 raised to k plus x plus 2 raised to k minus x, and simplifying, remove the grouping symbol. Here, x and minus x is 0. So we have 2 times 2 raised to k for the sum here. Now, simplifying this 2 is implied to have an exponent of 1, and we are multiplying exponential number with the same base, we add their exponents. This means that if we add 1 plus 615, 3 plus 205, 5 plus 123, and 15 plus 41, this sum here must be in the form 2 raised to k plus 1. And among these four numbers here, only 128 is a power of 2, because that is equal to 2 raised to the 7th. All the rest cannot be written in this form. And this 2 raised to the 7th can now be equated to 2 raised to k plus 1, giving us now the value of k to be equal to 6. So if k is 6, 6 plus 1 is 7, we have a correct equation here. And we now have our value for k. So this k is 6, this k is 6. We can now find the value of x. That happens when the factors of this 615 are 123 times 5, or 5 times 123. This means that this first factor can be equated to 123, the second factor to 5, and we have now these two equations. K is 6, so let's substitute 6 for k. 2 to the 6th is 64. Copy all the rest. And solving for x, we subtract 64 from both sides to get x equals 59. We now have one value for x. Solving the second equation, again, k is equal to 6. 2 to the 6th is 64. And simplifying, x is equal to 59 as well. So both of these equations resulted to x equals 59 when k is equal to 6. So if x is 59, we can now find the value of y. Using the given equation, 615 plus 59 squared equals 2 raised to y. Here, our x now is replaced by the computed x value of 59. The rest are arithmetic computation. Then adding the left side, that is equal to 4096 equals 2 raised to y. And 4096 is 2 raised to the 12th, so y is equal to 12. When x is equal to 59, and we now have this ordered pair. Now let's take the case when the first factor is equal to 5 and the second factor is equal to 123. And we arrive at these two equations again. And similarly solving for x, we found that x is negative 59, and for the second equation, x is also negative 59. And solving now for y, when x equals negative 59, we take the original equation again and substitute negative 59 for x. Solving now for y, we arrive at the same value, y equals 12, because negative 59 times negative 59 becomes positive 3,481. This gives us again another ordered pair solution to our Diophantine equation. So these are now the two ordered pairs. Going back to our visualization, 5912 is this point, negative 5912 is this point, and these are the only ordered pair solution that are both integers. All the other points in this red curve are either both non-integer or at least one of them is not integer, and they are excluded from the solution. We only want the ordered pair when both the x and the y coordinates are both integers. And to check our solution, the original equation is 615 plus x squared equals 2 raised to y. Our y is 12, so 2 to the 12 is 4096. Then the left side, 615 plus 59 squared is also 4096. And when x is negative 59, the left side is again 4096. So it's verified that our solution is correct. And we also showed in the process that these are the only integer solutions to this problem. Bye for now.